In the beginning, there was nothing. No light, no darkness, no space to fill, no time to measure, just nothing. Yet here we are, surrounded by billions of stars, countless galaxies, and the vast cosmic web that stretches across unimaginable distances. How did all of this come to exist from absolutely nothing? Tonight, we embark on a journey to explore the most profound mystery that has ever captivated the human mind. We will venture into the deepest questions of existence itself, questioning the very fabric of reality and the moment when everything we know began. Close your eyes for a moment and try to imagine complete nothingness. This is perhaps the most difficult thing a human mind can attempt to do. We are surrounded by something at every moment of our lives. Even in the darkest room, there is still space around us. Even in the quietest moment, there are still atoms vibrating, energy flowing, time passing. But true nothingness is different. It is not empty space, because even empty space is something. It is not darkness, because darkness exists only in contrast to light. It is not silence, because silence requires space for sound to not exist within. True, nothing means no space, no time, no energy, no matter, no dimensions, no possibilities. It means the complete and total absence of everything that could ever be, ever was, or ever might be. This concept is so alien to our experience that our brains struggle to grasp it. We live in a world of constant sensation, where every moment brings new input from our surroundings. We breathe air, we feel gravity, we see light, we hear sounds. The idea of absolute nothingness is like trying to imagine a color that does not exist, or trying to remember a time before we were born. Yet from this incomprehensible state of absolute nothingness, our entire universe somehow burst into existence. In a moment so brief that it lasted less than a trillionth of a trillionth of a trillionth of a second, everything we know came to be. The explosion was so violent and so complete that it created space itself. It created time itself. It created the very laws of physics that govern our reality. Every atom in your body was forged in that primordial fire. Every breath you take contains particles that have existed since the first moments after creation. Every star that lights the night sky, every planet that orbits those stars, every grain of sand on every beach, every drop of water in every ocean, all of it traces back to that single, mysterious moment we call the Big Bang. But here lies the greatest puzzle that has ever confronted human intelligence. If there truly was nothing before the beginning, then what could have possibly sparked the creation of everything? What force could have existed in a realm where no forces were possible? What energy could have ignited creation when no energy existed? What mysterious mechanism could have triggered the birth of space and time themselves when there was no space for mechanisms to exist and no time for triggers to occur? This question strikes at the very heart of what it means to exist. It challenges every assumption we have about cause and effect, about beginnings and endings, about the nature of reality itself. It forces us to confront the possibility that our universe, vast and ancient as it is, might be just one small part of something even more incomprehensible. As we explore this cosmic mystery together tonight, we will journey through the strange realm of quantum physics, where particles can appear from nowhere and disappear into nothing. We will venture into the theoretical landscapes of multiple universes, where our reality might be just one bubble in an infinite sea of possibilities. We will contemplate ideas that stretch the very limits of human imagination and challenge everything we thought we knew about existence. We will discover that even in what we call empty space, reality is far more active and mysterious than it appears. We will learn that the deepest void may not be empty at all, but alive with invisible forces and hidden potentials. We will explore theories that suggest our universe might have always existed in some form, cycling through endless phases of expansion and contraction, creation and destruction. And we will grapple with the humbling possibility that some questions may be forever beyond human understanding, not because we lack intelligence, but because the answers exist in realms that transcend the very categories of thought and language that make us human. So settle in beneath the quiet stars and let your mind wander into the infinite mystery that surrounds us. Tonight, we ask the ultimate question that has haunted philosophers and scientists for generations. If there was nothing, absolutely nothing at all, what sparked the Big Bang? What does it truly mean for nothing to exist? This question has puzzled philosophers for thousands of years and continues to challenge our greatest scientific minds today. When we try to imagine nothing, our brains immediately fill the void with something. We picture empty space, or darkness, or silence. But these are all forms of something, not nothing. Think about the emptiest place you can imagine. Perhaps it is the space between stars, stretching across billions of kilometers of apparent void. But even this seemingly empty region is filled with invisible particles, magnetic fields, and the faint radiation left over from the Big Bang itself. There are hydrogen atoms scattered throughout this space, perhaps only 1 atom per cubic meter, but they are still there. There are photons of light traveling at incredible speeds, carrying energy across the cosmos. There are neutrinos, ghostly particles that barely interact with matter, streaming through this space by the trillions every second. Even in the deepest reaches of space, beyond the influence of any star or galaxy, there is always something there. The fabric of space itself vibrates with gravitational waves, ripples in reality caused by massive objects accelerating somewhere in the universe. There are magnetic fields threading through the cosmic web, invisible highways that guide the motion of charged particles across unimaginable distances. Now imagine going further. Imagine removing every particle, every field, every trace of energy from this space. Strip away the hydrogen atoms, silence the photons, halt the neutrinos, smooth out the gravitational waves, and eliminate the magnetic fields. What remains? We might think we have achieved nothingness, but we still have space itself. Space is something. It has dimensions. It can expand and contract. It can curve and bend under the influence of matter and energy. So even empty space is not truly nothing. Space has properties that we can measure and describe. It has geometry. It can be flat or curved, finite or infinite. It can stretch and compress like a fabric. Scientists have discovered that space itself is expanding, carrying galaxies away from each other at speeds that increase with distance. This expansion is not objects moving through space, but space itself growing larger, creating more room between distant galaxies. To approach true nothingness, we must remove space itself. We must imagine a state where there are no dimensions, no up or down, no left or right, no here or there, no inside or outside. But even then, we still have time. Time allows for the possibility of change, for moments to pass, for events to unfold, for causes to lead to effects. Time gives meaning to words like before and after, beginning and end. So to reach absolute nothingness, we must remove time as well. But what happens when we remove both space and time? We enter a realm that is literally unimaginable, because imagination itself requires time to unfold and space to contain ideas. Our thoughts exist in time, flowing from one moment to the next. Our concepts require mental space to develop and connect with other ideas. Without space and time, there is no framework for thought, no stage for possibilities to play out, no context for existence to have any meaning. We are left with a concept that exists at the very edge of human understanding, a state so foreign to our experience that we lack the words to properly describe it. Every word we use, every metaphor we create, every comparison we make assumes the existence of space and time. How can we describe something that exists outside the very categories that make description possible? This is what philosophers call absolute nothingness. It is not merely the absence of things, but the absence of the very possibility of things. It is not a place where nothing exists, because there is no place. It is not a time when nothing happened, because there is no time. It is not even a state of being, because being itself implies existence, and existence requires some framework within which to be real. The ancient Greek philosopher Parmenides argued that such nothingness was not just difficult to imagine, but logically impossible. In his view, nothingness could not exist because the very statement, "nothing exists," contains a contradiction. How can nothing exist? To exist is to be something, and nothing is precisely not something. He concluded that something must have always existed, because the alternative led to logical absurdity. Other Greek thinkers like Democritus took a different approach. They argued that the universe consisted of atoms moving through void, and that this void was a kind of nothingness that made motion and change possible. Without empty space between atoms, they reasoned, nothing could move, and everything would be locked in place. In their view, nothingness was not just possible, but necessary for the world to function as we observe it. Centuries later, medieval philosophers struggled with similar questions. They wondered whether God could create absolute nothingness, and whether such an act would be a contradiction of divine power. Some argued that nothingness was beyond even divine capability, because it represented a logical impossibility. Others suggested that nothingness was the natural state from which God's creative power brought forth existence. Eastern philosophical traditions approach the question differently. In Buddhist thought, the concept of emptiness does not mean nothingness in the Western sense, but rather the absence of inherent, independent existence. Everything exists in relationship to everything else, with no fixed, permanent essence. This emptiness is not a void, but rather the fundamental nature of reality itself. Modern science has given us new ways to think about nothingness, but it has also made the concept even more mysterious and complex. We have discovered that what we call empty space is actually alive with activity. The quantum vacuum, the closest thing to nothingness that physics can describe, is far from empty. In the quantum world, pairs of particles constantly pop into existence and disappear again in time frames so brief that they exist at the very edge of what can be measured. These virtual particles borrow energy from the vacuum itself, live for incredibly short moments, and then annihilate each other, returning the borrowed energy. This process happens everywhere, all the time, even in the deepest void between galaxies. These quantum fluctuations reveal that even in the emptiest vacuum we can create in our laboratories, there is still something happening. The laws of quantum mechanics themselves seem to prevent true nothingness from existing. Even in the absence of all matter and energy, the quantum field remains, vibrating with invisible potential, ready to give birth to particles at any moment. The Heisenberg uncertainty principle tells us that we cannot know both the energy and the time of a quantum system with perfect precision. This fundamental limitation of measurement means that the vacuum can borrow energy for short periods without violating the laws of physics. The shorter the time, the more energy can be borrowed. In the briefest instance, enormous amounts of energy can appear from nowhere and disappear just as quickly. This raises profound questions about the nature of nothingness. If our deepest understanding of physics suggests that true nothingness cannot exist, then what are we really asking when we wonder what came before the Big Bang? Are we asking about a state that is fundamentally impossible, or are we asking about something else entirely? Perhaps what we call nothing is not the absence of everything, but rather the presence of pure potential. Perhaps nothingness is not empty but full, not barren but fertile, not the end of possibility but the beginning of all possibilities. Maybe what we mistake for emptiness is actually a state of perfect balance, where all possibilities exist simultaneously, cancelling each other out until something breaks the symmetry and allows reality to unfold. Some scientists have suggested that what we call nothingness might actually be a state of perfect symmetry, where all forces balance each other so completely that they appear to cancel out. In this view, the Big Bang was not the creation of something from nothing, but rather the breaking of this perfect symmetry, allowing the hidden richness of reality to unfold into the universe we observe today. Others propose that nothingness is simply a limitation of our language and thinking. They argue that the question itself is based on false assumptions about the nature of existence and causation. In their view, the universe does not need to come from something or nothing, because the very concept of coming from something else may not apply at the deepest levels of reality. These ideas stretch our minds to their limits. They force us to question not just what we know about the universe, but how we know anything at all. They remind us that the deepest mysteries of existence may require us to abandon our everyday ways of thinking and embrace concepts that feel alien to our human experience. Consider how difficult it is for us to truly understand even the simplest quantum phenomena. We are creatures evolved to navigate a world of medium-sized objects, moving at moderate speeds. Our intuitions are calibrated for a reality where things have definite locations, where cause clearly precedes effect, where something cannot be in two places at once. Yet the quantum world operates by entirely different rules, rules that seem to violate everything our common sense tells us about reality. If we struggle to understand the quantum world, which at least exists within space and time, how much more difficult is it to understand a state that exists outside space and time entirely? We are trying to use minds that evolved within the universe to understand what might have existed before the universe. We are using concepts that developed within space and time to grasp something that transcends both. Yet even as we acknowledge these limitations, we cannot escape the fundamental wonder that drives our inquiry. Here we are, conscious beings in a vast universe, pondering our own existence and the mystery of how consciousness itself could emerge from whatever came before. We are matter that has become aware of itself, atoms that have learned to contemplate, atoms, beings made of star stuff, questioning the origin of stars. Whether we call it nothing or something else entirely, the state that preceded our universe remains one of the most profound puzzles in all of science and philosophy. It is a mystery that connects the largest questions about the cosmos with the deepest questions about the nature of existence itself. It forces us to confront the possibility that reality is far stranger and more wonderful than we ever imagined. If there truly was nothing, it is a state beyond our understanding, beyond our language, and perhaps beyond our ability to ever fully comprehend. Yet in confronting this mystery, we touch something essential about what it means to be human. We are the beings who ask why there is something rather than nothing. We are the universe becoming conscious of itself, reality questioning its own existence. And in that question lies the beginning of all wisdom and the foundation of all wonder. The mystery of nothing illuminates everything we will discover about the Big Bang, about the birth of space and time, and about the deepest nature of reality itself. In the contemplation of absolute nothingness, we find the seeds of everything that is, was, or ever could be. As we continue our journey through the cosmos tonight, we carry this profound mystery with us. The concept of nothing will illuminate everything we discover about the Big Bang, about the birth of space and time, and about the deepest nature of reality itself. In the mystery of nothing, the story of everything begins. 13.8 billion years ago, everything that exists in our universe today was compressed into a point smaller than the period at the end of this sentence. In that infinitesimal speck, all the matter and energy that would eventually become billions of galaxies, trillions of stars, and countless planets was contained in a state so dense and so hot that it defies our ability to comprehend. Then, in an instant that lasted less than a trillionth of a trillionth of a trillionth of a second, this point began to expand. But this was not an explosion in the way we normally think of explosions. When a bomb explodes, it sends matter flying outward through existing space. The Big Bang was something far more fundamental and strange. It was the creation of space itself. Imagine trying to watch the Big Bang unfold. You cannot, because there was no place to stand and watch from. There was no outside perspective, because there was no outside. Space itself was being born, expanding from nothing into something, creating the very stage upon which all future cosmic dramas would play out. In the first moments after the Big Bang began, the universe expanded faster than the speed of light. This might seem impossible, since Einstein showed us that nothing can travel faster than light through space. But the universe found a loophole in this cosmic speed limit. While nothing can move through space faster than light, space itself has no such restriction. Space can expand as quickly as it wants, carrying everything within it along for the ride. This period of incredibly rapid expansion is called cosmic inflation. In a time period so brief that it makes a blink of an eye seem like an eternity, the universe grew from smaller than a proton to larger than a basketball. But even this comparison fails to capture the true scale of what happened. During inflation, the universe expanded by a factor of at least 10 to the 26th power. That means it grew larger by a number with 26 zeros after it. To understand how dramatic this expansion was, imagine a grain of sand suddenly growing to be larger than the observable universe today. Even this mind-boggling comparison understates what happened during inflation. The universe did not just grow large, it grew unimaginably, incomprehensibly, fantastically large, in the tiniest fraction of a second. During this violent birth, the universe was unimaginably hot. In the first moment, temperatures reached 10 to the 32nd power degrees. This is so hot that atoms could not exist. Even the protons and neutrons that make up atomic nuclei could not hold together. The universe was filled with a soup of fundamental particles, quarks and leptons, swimming in a sea of pure energy. As the universe expanded, it began to cool, like any gas expanding into a larger volume. But even as it cooled, it remained far hotter than anything we can imagine. After 1 second of expansion, the temperature had dropped to a mere 10 billion degrees. This was still hot enough to prevent the formation of most atomic nuclei, but cool enough for protons and neutrons to begin sticking together. This was the era of Big Bang nucleosynthesis, when the first atomic nuclei formed. For about 20 minutes, the universe was like a gigantic nuclear furnace, fusing protons and neutrons into the light elements. Hydrogen nuclei, which are just single protons, were already present. But now, helium nuclei began forming, along with tiny amounts of lithium and beryllium. The process was remarkably efficient. About 25% of all the normal matter in the universe was converted into helium during those first 20 minutes. The rest remained as hydrogen. Heavier elements like carbon, oxygen, and iron would have to wait billions of years to be forged in the hearts of stars. After about 20 minutes, the universe had expanded and cooled enough that nuclear fusion stopped. The cosmic furnace shut down, leaving the universe filled with a hot, glowing plasma of hydrogen and helium nuclei mixed with free electrons. This plasma was opaque to light, like a thick fog that prevents us from seeing very far. For the next 380,000 years, the universe remained in this opaque state. Light could not travel far before being absorbed or scattered by the free electrons. The universe was dark, not because there was no light, but because the light could not travel freely through the cosmic fog. Then, as the universe continued to expand and cool, something remarkable happened. The temperature dropped low enough for electrons to combine with atomic nuclei, forming the first complete atoms. This moment is called recombination, though it was actually the first time atoms had ever formed, not a reunion. When recombination occurred, the cosmic fog suddenly cleared. Light could now travel freely through space, for the first time in the universe's history. The universe became transparent, and the trapped light was released to travel across the cosmos. This light, stretched and cooled by billions of years of cosmic expansion, still fills the universe today. We call it the cosmic microwave background radiation. The cosmic microwave background is like the afterglow of creation itself. When we detect this radiation with our telescopes, we are seeing the universe as it was when it first became transparent, nearly 14 billion years ago. We are looking back in time to witness the moment when the cosmic fog lifted and the universe lit up for the first time. This ancient light carries within it the imprint of tiny variations in density that existed when the universe was young. Some regions were slightly denser than others, and these small differences would eventually grow into the large-scale structure we see today. The denser regions attracted more matter through gravity, eventually collapsing to form the first stars and galaxies. But in those early days after recombination, the universe was a much simpler place. There were no stars, no galaxies, no planets, no complex chemistry, no life. Just hydrogen and helium atoms drifting through the expanding cosmos, slowly gathering together under the influence of gravity. The universe entered what cosmologists call the Dark Ages, not because it was evil or foreboding, but because there were no sources of light. The afterglow of the Big Bang was fading as it was stretched by expansion, and the first stars had not yet formed. For hundreds of millions of years, the universe was truly dark. During this time, gravity was slowly doing its work. The tiny variations in density left over from the Big Bang were growing larger. Matter was clumping together, forming the first structures in the universe. These were not yet stars or galaxies, but vast networks of dark matter and gas that would eventually become the scaffolding upon which all future cosmic structure would build. Dark matter, which makes up about 85% of all matter in the universe, played a crucial role in this process. Unlike normal matter, dark matter does not interact with light or ordinary matter except through gravity. This allowed it to begin clumping together earlier than normal matter, creating gravitational wells that would eventually trap gas and lead to star formation. The first stars began forming when the universe was only a few 100 million years old. These were very different from the Sun and other stars we see today. They were much more massive, much hotter, and much shorter lived. They contained almost no elements heavier than hydrogen and helium, because heavier elements had not yet been created. When these first massive stars exhausted their nuclear fuel, they exploded as supernovae, scattering the heavy elements they had created in their cores throughout the surrounding space. These elements, forged in the nuclear furnaces of stellar cores and the violent explosions of supernovae, would become the building blocks for planets and eventually for life itself. As more generations of stars formed and died, the universe became enriched with heavier elements. Galaxies began to take shape as gravity organized matter into increasingly complex structures. Star formation continued at an ever-increasing rate, illuminating the cosmos and bringing the Dark Ages to an end. The Big Bang Theory explains not just how the universe began, but how it evolved from a simple, hot, dense state into the rich, complex cosmos we observe today. It explains why the universe is expanding, why it is filled with a particular mix of hydrogen and helium, why there is cosmic microwave background radiation, and why the large-scale structure of the universe looks the way it does. This theory represents one of the greatest intellectual achievements in human history. It reveals that our universe has not always existed in its current form, but has a definite beginning and a long, fascinating history of change and evolution. It shows us that we are not just observers of the cosmos, but participants in an ongoing cosmic story that began nearly 14 billion years ago. Yet for all its explanatory power, the Big Bang Theory also presents us with deep mysteries. It tells us what happened from the first fraction of a second onward, but it cannot tell us what happened at the very beginning, at time zero itself. It describes the expansion of space, but it cannot explain what caused that expansion to begin. The Big Bang is not an explosion in space, but the creation of space itself, a sudden expansion from a point where all our known laws of physics seem to collapse and cease to make sense. In that singular moment, time and space and matter and energy all came into existence together, emerging from a state that lies beyond our current understanding. As we contemplate this cosmic origin story, we are left with the same profound question we began with. If the Big Bang was the beginning of everything, what came before it? What existed in that unimaginable state before space and time themselves were born? And what could have possibly triggered this spectacular birth of reality itself? At the heart of the Big Bang Theory lies perhaps the most mysterious concept in all of physics, the singularity. When we trace the expansion of the universe backward in time, following the cosmic story in reverse, we arrive at a moment where all our understanding breaks down. This is the singularity, a point of infinite density and infinite curvature of space, where the laws of physics as we know them simply cease to apply. To understand what a singularity means, imagine watching a movie of cosmic expansion played in reverse. Galaxies rush toward each other, stars crowd together, space itself contracts. The universe becomes smaller and smaller, denser and denser, hotter and hotter. Temperature and density climb toward impossible values as we approach the moment of the Big Bang. But what happens when we reach that moment itself? According to the mathematics of general relativity, all the matter and energy in the observable universe, everything that would eventually become billions of galaxies containing trillions of stars, was compressed into a single point of zero size. Not just very small, but actually zero. A point with no dimensions, no width, no height, no depth, yet containing everything that exists. This mathematical point is what physicists call a singularity. It represents a place where the equations that describe our universe give infinite answers to finite questions. The density becomes infinite. The temperature becomes infinite. The curvature of space becomes infinite. These infinities signal that our theories have reached their limit, that we are trying to describe something that lies beyond the reach of our current understanding. But here is where the mystery deepens. A singularity is not really a thing in the way we normally think of things. It is not an object that exists in space and time. Rather, it represents the absence of space and time themselves. At the singularity, there is no space for anything to exist within, no time for any process to unfold. In a very real sense, the singularity represents a state where existence itself has no meaning. This creates a profound paradox. How can we say that all the matter and energy in the universe was contained in the singularity if the singularity itself has no size and no duration? How can something that does not exist in space or time contain everything that does exist in space and time? It is like trying to pour an ocean into a container that has no volume. The answer, according to our best current understanding, is that space and time themselves were created at the moment of the Big Bang. The singularity does not exist within space and time. Rather, space and time emerge from the singularity. This means that the very stage upon which all physical processes play out, the fundamental arena of existence itself, came into being in that first moment. Think about what this implies. Before the Big Bang, there was no before, because time itself did not exist. There was no place where the singularity existed, because space itself had not yet been created. The concepts of before and after, here and there, cause and effect, all of these depend on the existence of space and time, and therefore have no meaning when applied to the singularity itself. This is why physicists say that asking what came before the Big Bang is like asking what is north of the North Pole. The question itself is based on a misunderstanding of the nature of what we are asking about. Just as there is no direction north of the northernmost point on Earth, there may be no time before the first moment of time. Yet this explanation, satisfying as it may be mathematically, leaves us with an even deeper mystery. If space and time came into existence at the Big Bang, what can we say about the nature of existence itself at that moment? Was the singularity a state of being or a state of nothingness? Can something that exists outside of space and time be said to exist at all? Some physicists argue that the singularity represents the ultimate nothingness, a state where not only matter and energy are absent, but where the very concepts of existence and non-existence break down. In this view, the Big Bang was not the explosion of something that already existed, but rather the spontaneous emergence of existence itself from a state that cannot be described as either something or nothing. Others suggest that the singularity is not really nothing, but rather everything in a state of perfect unity. All the diversity we see in the universe today, all the different particles and forces and structures, were present in the singularity in a completely unified form. The Big Bang was then not the creation of something from nothing, but the breaking of this perfect unity into the multiplicity of forms we observe. This idea echoes ancient philosophical concepts about the nature of ultimate reality. Many traditions have spoken of a primordial unity from which all diversity emerges, a state of pure being that contains all possibilities, but manifests none of them until some cosmic process causes it to differentiate and become the many things we see around us. Modern physics gives us new ways to think about these ancient ideas. In quantum field theory, we learn that what we call empty space is actually filled with quantum fields that permeate all of reality. These fields exist even in the absence of particles, representing a kind of potential energy that underlies all physical processes. Perhaps the singularity represents a state where all these quantum fields exist in perfect equilibrium, where all possibilities are present, but none are actualized. The Big Bang might then be understood as a kind of cosmic symmetry breaking, where this perfect balance was disturbed and the hidden richness of reality began to unfold. But even this picture may be too simplistic. The truth is that our current theories of physics break down completely when we try to describe the singularity. General relativity, which gives us our best description of gravity and the large-scale structure of space and time, predicts that a singularity must have existed at the beginning of the universe. But general relativity also tells us that its own predictions become meaningless at the singularity. This is because general relativity is a classical theory, meaning it does not take into account the quantum nature of reality. At the enormous densities and energies present near the Big Bang, quantum effects become crucially important. We need a theory of quantum gravity to properly describe what happens in these extreme conditions, but such a theory does not yet exist. The singularity, therefore, represents the boundary of our current knowledge. It is the place where our most successful theories encounter their own limitations and point beyond themselves toward a deeper understanding that we have not yet achieved. In confronting the singularity, we are forced to acknowledge that there are aspects of reality that remain profoundly mysterious. Some physicists believe that when we finally develop a complete theory of quantum gravity, the singularity will disappear from our description of the Big Bang. Instead of infinite density and zero size, we might find that the universe began in some finite but extremely dense and hot state. The singularity might turn out to be an artifact of our incomplete understanding rather than a real feature of physical reality. String theory, one of the most promising approaches to quantum gravity, suggests that the fundamental constituents of reality are not point particles, but tiny vibrating strings. In string theory, there may be a minimum possible size, a quantum of space itself, below which the very concept of size becomes meaningless. If this is true, then the universe could not have been compressed to a true mathematical point, but only to this minimum size. Loop quantum gravity, another approach to understanding the quantum nature of space and time, suggests that space itself is made up of discrete units, like pixels on a computer screen, but unimaginably smaller. In this picture, the Big Bang might have been preceded by a big bounce, where a previous universe collapsed down to the minimum possible size and then expanded again to become our universe. These ideas remain highly speculative, but they point toward the possibility that the singularity is not the end of the story, but rather a sign that we need to dig deeper. They suggest that the apparently impossible state at the beginning of the universe might be resolved when we achieve a more complete understanding of the quantum nature of reality. Yet even if the singularity turns out to be replaceable by some more complete description, the fundamental mystery remains. Whether the universe began from a mathematical singularity, a quantum bounce, a string theory brain collision, or some other exotic process, we are still left with the question of why anything exists at all. The singularity, whether real or apparent, serves as a powerful symbol of the limits of human knowledge and the deep mystery that surrounds the origin of everything we know. It represents a boundary between the knowable and the unknowable, between the territory that science has mapped and the vast unexplored regions that may forever lie beyond our reach. In contemplating the singularity, we are confronting the deepest questions about the nature of existence itself. We are asking not just how the universe began, but what it means for anything to begin, what it means for something to exist, and what it means for us to be conscious beings capable of pondering these ultimate mysteries. The singularity stands at the threshold between being and non-being, between something and nothing, between the knowable and the unknowable. It is both everything and nothing, the source of all existence and the negation of existence itself. In trying to understand it, we reach the very limits of human thought and touch something that may be forever beyond our comprehension. As we continue our journey through the deepest mysteries of cosmology, we carry with us this profound enigma. The singularity reminds us that at the heart of our scientific understanding lies a mystery as deep as any that has ever challenged human thought. In seeking to understand the beginning of everything, we discover that the beginning itself may be a concept that transcends understanding. The question haunts us with its apparent simplicity and profound depth. What came before the Big Bang? It seems like the most natural question to ask about any event, especially one as momentous as the birth of the entire universe. Yet this innocent inquiry leads us into some of the strangest territory that human thought has ever explored. When we ask what came before something, we are assuming that time flows like a river, with a clear sequence of moments, leading from past to present to future. We imagine that events unfold one after another in an orderly progression, each moment building upon what came before. This assumption works perfectly well for everything we experience in our daily lives, but it may break down completely when we try to apply it to the origin of the universe itself. If time itself was created at the moment of the Big Bang, then the very concept of before becomes meaningless. It would be like asking what happened before the first moment of time. The question contains its own contradiction, because before implies an earlier time, and if there was no earlier time, then there was no before. Yet our minds rebel against this answer. Surely something must have existed to give rise to the Big Bang. Surely there must have been some cause, some trigger, some prior state that led to the explosion of space and time. Our entire experience of reality is built around the idea that everything has a cause, that nothing happens without something else making it happen. This leads us to one of the most fundamental questions in all of philosophy and science. Must everything have a cause, or are there some things that can happen spontaneously, without any prior cause whatsoever? If everything must have a cause, Then what caused the Big Bang? And what caused the cause of the Big Bang? This line of reasoning leads to an infinite regress, an endless chain of causes stretching back forever. Some thinkers have embraced this infinite regress, arguing that the universe must be eternal, without beginning or end. In their view, there was no Big Bang in the sense of an absolute beginning, but rather a transformation from some previous state. The universe has always existed in some form, cycling through different phases of expansion and contraction, creation and destruction. This idea leads us to the concept of the Big Bounce. Instead of emerging from nothing, our universe might be the result of a previous universe that collapsed in on itself, compressing down to an incredibly dense state before bouncing back and expanding again. In this cyclical model, the Big Bang was not the beginning of everything, but simply the most recent in an endless series of cosmic cycles. Imagine the universe as a cosmic balloon that inflates and deflates repeatedly. Each cycle begins with rapid expansion, continues through a long period of slower expansion, then reverses into contraction as gravity eventually wins out over the expanding force. The universe collapses back toward a point of maximum compression, but instead of forming a true singularity, quantum effects cause it to bounce back and begin expanding again. This bouncing universe model solves the problem of what came before the Big Bang by suggesting that there was no absolute beginning. Time stretches infinitely into the past, filled with an endless sequence of cosmic cycles. Each bounce creates what appears to be a new universe, but is actually just the continuation of an eternal cosmic process. Yet this solution creates its own mysteries. If the universe has been bouncing forever, why does each cycle produce the same fundamental laws of physics? Why do the forces of nature maintain their strengths from one cycle to the next? And how do we explain the remarkable fine-tuning of physical constants that allows complexity and life to emerge? Another approach to the question of what came before involves the concept of eternal inflation. This theory suggests that our observable universe is just one small region in a vast, possibly infinite realm where space is constantly expanding and giving birth to new cosmic domains. In the eternal inflation model, what we call the Big Bang was actually just a local event in a much larger process. Somewhere in the infinite expanse of inflating space, a small region stopped inflating and began the more sedate expansion we observe in our universe today. But the larger inflationary process continues, constantly creating new regions that will undergo their own local Big Bangs. This picture suggests that our universe had no single beginning, but emerged from an eternal process that has no start and no end. The inflation field that drives this process exists in a state of eternal activity, constantly spawning new universes in an infinite cosmic landscape. What came before our Big Bang was simply more of this eternal inflationary process, stretching back infinitely in time. But eternal inflation raises its own puzzles. What sustains the inflation field? Where did the inflating space itself come from? And how do we explain the existence of the physical laws that govern the inflationary process? Even if our universe emerged from eternal inflation, we still face the question of what gave rise to the eternal inflationary multiverse itself. Some physicists have proposed that the answer lies in quantum mechanics and the strange behavior of quantum fields. At the deepest level, reality consists of quantum fields that permeate all of space. These fields are subject to quantum fluctuations, spontaneous changes in energy that occur without any external cause. Perhaps the entire universe emerged from such a quantum fluctuation. In this view, what came before the Big Bang was not nothing in the absolute sense, but rather the quantum vacuum, a state where quantum fields exist but no particles are present. This quantum vacuum is not truly empty, but filled with potential, constantly giving rise to virtual particles that appear and disappear in the briefest instants. The idea is that our entire universe might be the result of an unusually large quantum fluctuation, a random event in the quantum foam that gave rise to space, time, matter, and energy. This would mean that the Big Bang was not caused by anything in the traditional sense, but was simply a spontaneous quantum event, no different in principle from the virtual particles that constantly pop into existence throughout space. This quantum origin story has a strange beauty to it. It suggests that the universe is not the result of some grand design or cosmic purpose, but rather emerged from the fundamental randomness that underlies all quantum processes. The most important event in cosmic history, the birth of everything we know, would then be no different from the countless quantum events happening in every cubic centimeter of space at every moment. Yet even this picture leaves questions unanswered. Where did the quantum fields themselves come from? What determines the laws of quantum mechanics that govern their behavior? And why does the quantum vacuum have the particular properties that allow universes to emerge from fluctuations? Another possibility is that our universe emerged from a collision between higher dimensional objects called branes. In some versions of string theory, our three-dimensional space is actually a brane, a membrane floating in a higher dimensional realm. Occasionally, these branes collide with each other, and such collisions could give rise to what appears to us as a Big Bang. In this scenario, what came before the Big Bang was the slow approach of two branes through higher dimensional space. The collision between these branes released enormous amounts of energy, creating the hot, dense state from which our universe expanded. The branes then separated again, leaving behind the expanding universe we observe today. This brane collision model suggests that our universe is part of a much larger multiverse, a vast higher dimensional space populated by many branes. From time to time, these branes interact, giving rise to new universes through their collisions. What we experience as the beginning of everything might be just a local event in this much grander cosmic arena. Yet again, this pushes the ultimate questions back one more level. Where did the higher dimensional space come from? What created the branes that float within it? And what governs the physics of this higher dimensional realm? Each answer seems to require another question, leading us deeper into mystery rather than closer to resolution. Perhaps the most radical possibility is that the question itself is meaningless. Some physicists and philosophers argue that asking what came before the Big Bang is like asking what is north of the North Pole, or what color is the number 7. These are grammatically correct questions, but they make assumptions about reality that turn out to be false. If time itself was created at the Big Bang, then there literally was no before. The universe did not emerge from some previous state because there were no previous states. It did not arise at some particular moment because there were no moments before it arose. The Big Bang was not an event in time, but the creation of time itself. This perspective suggests that we need to fundamentally revise our understanding of causation and existence. Perhaps not everything needs a cause. Perhaps some things can simply exist without explanation, without prior conditions, without emerging from something else. Perhaps the universe is what philosophers call a brute fact, something that exists for no reason other than that it does exist. This idea challenges our deepest intuitions about reality. We are creatures who have evolved to understand the world in terms of cause and effect, to trace every event back to its origins. But perhaps this way of thinking, so useful for navigating our everyday world, breaks down when applied to the deepest questions about existence itself. Consider the possibility that existence is more fundamental than non-existence. Perhaps the natural state of reality is for things to exist, and the question we should be asking is not why there is something rather than nothing, but why we expect there to be nothing rather than something. Maybe existence requires no explanation because it is the most basic feature of reality itself. Or perhaps the answer lies beyond the reach of human understanding. We are finite beings trying to comprehend infinite mysteries. Our brains evolved to help us survive in a world of medium-sized objects moving at moderate speeds, not to understand the ultimate nature of reality. Perhaps questions about what came before the Big Bang will forever exceed our cognitive limitations. Yet even if we cannot answer these questions definitively, we can still find wonder and meaning in contemplating them. In asking what came before the Big Bang, we are participating in the deepest human quest for understanding. We are exercising the remarkable capacity that consciousness gives us to question our own existence and to seek meaning in the vast mystery that surrounds us. The question of what came before the Big Bang remains one of the greatest unsolved puzzles in all of science and philosophy. Whether the answer involves eternal inflation, cyclic universes, quantum fluctuations, brane collisions, or something we have not yet imagined, it will surely transform our understanding of reality in ways we cannot predict. As we continue our journey through the cosmos tonight, we carry this profound mystery with us. The question of what came before reminds us that even our most successful theories point beyond themselves toward deeper mysteries. In seeking to understand the beginning of everything, we discover that the concept of beginning itself may be far stranger and more wonderful than we ever imagined. In the deepest reaches of space, in the most perfect vacuum that nature can provide, something extraordinary is always happening. Even where there appears to be absolutely nothing, where no particles exist and no energy flows, the fabric of reality itself is alive with constant, invisible activity. This is the realm of quantum fluctuations, where the very foundations of existence reveal themselves to be far stranger and more dynamic than our everyday experience could ever suggest. To understand how quantum fluctuations might have given birth to the universe, we must first understand what they are and why they occur. In the quantum world, the notion of empty space as a passive, unchanging void is revealed to be a classical illusion. What we call the vacuum is actually a seething ocean of potential, filled with quantum fields that permeate every cubic centimeter of space. These quantum fields are not things in the way we normally think of things. They are not objects that exist at particular locations, but rather invisible potentials that exist everywhere simultaneously. Each type of fundamental particle, from electrons to photons to quarks, has its own associated quantum field. When we observe a particle, we are actually seeing a localized excitation in its corresponding field, like a wave rising from the surface of an infinite ocean. But even when no particles are present, these fields continue to exist, and they are never completely still. The Heisenberg uncertainty principle, one of the fundamental laws of quantum mechanics, tells us that we cannot know both the energy of a quantum system and the duration of that energy state with perfect precision. This limitation is not just a practical problem with our measuring instruments, it is a fundamental feature of reality itself. Because of this uncertainty, quantum fields are constantly borrowing energy from the vacuum itself, using this borrowed energy to create pairs of virtual particles that exist for incredibly brief moments before annihilating each other and returning the borrowed energy. These virtual particles are not quite real in the sense that we can directly observe them, but they are real enough to have measurable effects on the physical world. The process happens everywhere, all the time, throughout the entire universe. In every tiny region of space, pairs of particles and antiparticles are constantly popping into existence, existing for a time so brief that it defies human imagination, and then disappearing again. The smaller the region of space and the shorter the time interval, the larger the energy fluctuations that can occur. This might seem like mere theoretical speculation, but quantum fluctuations have real, observable consequences. They affect the behavior of atoms, influence the decay rates of particles, and even cause a measurable force between closely spaced metal plates in a vacuum. The quantum foam, as physicists sometimes call this seething activity, is not just a mathematical abstraction, but a verified feature of reality. Now imagine what happens if we consider quantum fluctuations not just in ordinary space, but in the quantum realm that might have existed before space and time themselves were created. If there was some primordial quantum state before the Big Bang, it too would have been subject to fluctuations. And if the right kind of fluctuation occurred, it might have been powerful enough to create space, time, matter, and energy all at once. This is the remarkable possibility that some physicists have proposed. Perhaps our entire universe, with all its galaxies, stars, and planets, is the result of a quantum fluctuation that occurred in some pre-existing quantum realm. The Big Bang would not have been the emergence of something from nothing, but rather the emergence of our familiar space-time from a deeper, more fundamental quantum reality. The idea seems almost absurdly speculative, but it is based on well-established principles of quantum mechanics. We know that quantum fluctuations can create particles from the vacuum. The question is whether a large enough fluctuation could create not just particles, but the entire framework of space and time within which particles exist. To understand how this might work, we need to think about the relationship between matter, energy, and gravity. Einstein showed us that matter and energy are equivalent, related by his famous equation E equals mc squared. He also showed us that matter and energy curve space-time, creating what we experience as gravitational force. This means that if enough energy is concentrated in a small enough region, it can create significant curvature in space-time. Now consider what happens in a very large quantum fluctuation. If enough energy is borrowed from the quantum vacuum, it might curve space-time so severely that it begins to expand rapidly, creating its own space to exist within. This expansion would be the beginning of cosmic inflation, the rapid stretching of space that we believe occurred in the first moments after the Big Bang. But here is where the story becomes even more remarkable. As space expands during inflation, the energy of the quantum fluctuation gets spread out over a larger and larger volume. Normally, this would cause the energy density to decrease and the expansion to slow down and eventually reverse. But in certain theoretical models, the expansion itself can tap into additional energy sources, allowing the process to become self-sustaining. The inflating region creates its own space-time, generates its own matter and energy, and continues expanding at an accelerating rate. What began as a tiny quantum fluctuation becomes an entire universe, complete with all the space, time, matter, and energy needed to give rise to galaxies, stars, planets, and eventually life itself. This process might not be unique to our universe. If quantum fluctuations can give rise to one universe, they can give rise to many. The same quantum processes that created our universe might be constantly creating other universes, each emerging from its own primordial fluctuation in the quantum vacuum. This leads to the mind-boggling possibility of an infinite multiverse, where countless universes are constantly being born from the ceaseless activity of quantum fields. In this picture, our universe is not special or unique, but simply one bubble of space-time among countless others, each with its own Big Bang, its own history, and potentially its own laws of physics. We exist in this particular universe not because it was designed for us, but because it happens to have the right conditions for our kind of life to emerge. The quantum fluctuation theory also helps us understand one of the most puzzling features of our universe, the fact that it appears to be remarkably flat and uniform on large scales. When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we see tiny variations in temperature, but these variations are incredibly small, less than 1 part in 100,000. This uniformity is puzzling because different regions of the observable universe are so far apart that light has not had enough time since the Big Bang to travel between them. How can regions that have never been in contact with each other have almost exactly the same temperature? This is known as the horizon problem, and it suggests that our observable universe must have emerged from a much smaller, more uniform region. Cosmic inflation, potentially triggered by a quantum fluctuation, provides a solution to this puzzle. If our entire observable universe was once contained within a region small enough for light to cross, then all parts of it could have reached thermal equilibrium before inflation began. When inflation then stretched this tiny, uniform region to cosmic scales, it preserved the uniformity while creating the vast universe we observe today. The quantum fluctuation origin story also addresses another cosmic puzzle, the flatness problem. When we measure the geometry of space in our universe, we find that it is remarkably close to being perfectly flat. This is surprising because according to general relativity, the universe should curve either inward or outward depending on its total density. The fact that it is so close to flat suggests that its density is tuned to an incredibly precise value. Inflation provides a natural explanation for this flatness. Just as inflating a balloon makes its surface appear flatter to an ant crawling on it, cosmic inflation would have flattened any initial curvature in space-time, making the universe appear flat, regardless of what its initial geometry might have been. But perhaps the most remarkable aspect of the quantum fluctuation theory is what it suggests about the nature of existence itself. In this picture, the universe did not arise from some cosmic designer or external cause, but rather from the spontaneous, random activity that is built into the very foundations of reality. The most important event in cosmic history would then be no different in principle from the countless quantum events happening in every atom at every moment. This suggests a universe that is fundamentally creative and self-generating. Reality does not need an external source or prime mover, but carries within itself the capacity for spontaneous creation. The quantum vacuum is not empty but pregnant with possibilities, constantly giving birth to new realities through its own inherent activity. Yet even this remarkable picture leaves deep questions unanswered. Where did the quantum fields themselves come from? What determines the laws of quantum mechanics that govern their behavior? Why does the quantum vacuum have the particular properties that allow universes to emerge from fluctuations? In solving one mystery, we seem to create others. Some physicists have suggested that even the laws of physics themselves might emerge from deeper quantum processes. Perhaps what we call the fundamental constants of nature, things like the strength of gravity or the mass of the electron, are not fixed features of reality, but rather the result of quantum processes that unfold differently in different regions of the multiverse. This leads to the startling possibility that everything we observe, from the laws of physics to the existence of space and time themselves, might be the result of quantum fluctuations occurring at ever deeper levels of reality. In this view, there might be no ultimate foundation to existence, no final level where the questions stop. Reality might be quantum fluctuations all the way down. The quantum fluctuation theory represents one of the most radical and beautiful ideas ever proposed about the origin of the universe. It suggests that existence itself is an expression of the creative potential built into the deepest levels of reality. In the quantum world, nothing is truly nothing. Emptiness is full of possibility, and the void itself is alive with the power to create entire universes. As we contemplate this possibility, we are led to a profound realization about our place in the cosmos. If we and everything we know emerged from a quantum fluctuation, then we are not separate from the creative process that gave birth to the universe, but rather its latest expression. We are the universe becoming conscious of itself, quantum fields organized in such a way that they can contemplate their own existence. In the ceaseless dance of quantum fluctuations, in the endless creativity of the quantum vacuum, we glimpse something that might be even more fundamental than matter and energy. We see the universe as a self-creating, self-organizing, self-aware process, constantly bringing new realities into existence through its own inherent creative power. The mystery of existence transforms from a question about why there is something rather than nothing into a celebration of the infinite creativity that lies at the heart of being itself. Imagine a cosmic process so vast and so eternal that our entire observable universe, with its billions of galaxies stretching across 93 billion light-years, represents nothing more than a tiny bubble in an infinite ocean of space. Picture a mechanism so powerful and so persistent that it has been creating universes for an eternity, spawning countless cosmic domains, each with its own Big Bang, its own laws of physics, and its own evolutionary destiny. This is the extraordinary vision of eternal inflation, a theory that suggests our universe emerged not from absolute nothingness, but from an ongoing cosmic process that has no beginning and no end. In this picture, what we call the Big Bang was not the start of everything, but simply a local event in a much grander story, a brief transition in one small region of an eternally expanding multiverse. To understand eternal inflation, we must first understand the simpler concept of cosmic inflation that we believe occurred in the early moments of our universe. During the first tiny fraction of a second after the Big Bang, space itself expanded at a rate far faster than the speed of light, growing from subatomic scales to cosmic scales in an almost instantaneous burst of growth. This inflationary expansion was driven by a special kind of energy field called the inflaton field. Unlike ordinary matter and radiation, which become less dense as space expands, the inflaton field maintained a nearly constant energy density, even as space stretched. This constant energy density provided a kind of cosmic repulsion, pushing space apart with ever-increasing force and driving the rapid expansion we call inflation. But here is where the story becomes truly remarkable. The inflaton field that drove inflation in our universe might be just one small part of a much larger field that permeates a vast region of space. While inflation ended in our cosmic neighborhood, allowing our universe to enter the more sedate phase of expansion we observe today, the larger inflaton field might continue its relentless expansion in other regions. Picture an infinite landscape where the inflaton field has different values in different locations. In most of this landscape, the field remains trapped in a high-energy state, driving continued rapid expansion. But occasionally, in random locations scattered throughout this inflating space, the field drops to a lower energy state, causing inflation to end locally and creating what appears to observers in that region as a Big Bang. Each such event creates a pocket universe, a finite region of space-time that expands much more slowly than the surrounding inflating space. To beings living within such a pocket universe, it appears that their entire cosmos began with a Big Bang and has been expanding ever since. They have no direct way to observe the larger inflating space from which their universe emerged. Our universe would be one such pocket, created when the inflaton field happened to drop to a lower energy state in our particular region of space. The Big Bang we observe was not the beginning of space and time themselves, but rather the beginning of our local space-time, carved out from the larger, eternally inflating multiverse. This process of pocket universe creation never stops. As the larger inflaton field continues to expand, it constantly creates new regions of space where pocket universes can form. Each new pocket begins with its own apparent Big Bang and evolves according to whatever laws of physics happen to apply in that particular region of the multiverse. The mathematics of this process leads to a startling conclusion. Even though pocket universes are constantly forming, the volume of inflating space grows much faster than the volume occupied by pocket universes. This means that the proportion of space undergoing inflation actually increases over time, even as more and more pocket universes are created. Eternal inflation is thus truly eternal. No matter how many pocket universes form, there is always more inflating space to create new ones. The process has no end, and if the mathematics is correct, it also has no beginning. The inflating multiverse stretches infinitely into the future and infinitely into the past, an eternal cosmic engine constantly generating new realities. This vision transforms our understanding of existence in profound ways. Our universe, vast as it seems to us, becomes just one bubble among an infinite collection of bubbles, each representing a different experiment in cosmic evolution. Some of these bubble universes might be similar to ours, with similar laws of physics and similar evolutionary histories. Others might be radically different, with different fundamental forces, different particles, and different possibilities for complexity and life. The eternal inflation scenario also provides a new perspective on the question of why our universe has the particular properties we observe. The fundamental constants of nature, things like the strength of gravity, the mass of the electron, and the rate of cosmic expansion, all seem to be finely tuned to allow for the existence of stars, planets, and life. This fine-tuning has long puzzled scientists and philosophers. In an eternally inflating multiverse, this puzzle might have a simple solution. If different pocket universes have different values for their fundamental constants, then most pocket universes would be sterile, unable to support the complex chemistry needed for life. We observe a life-friendly universe not because it was designed for us, but because we could only evolve in a universe that happened to have the right properties for life to emerge. This is an application of what philosophers call the anthropic principle. We observe the universe to have life-friendly properties because we are here to observe it. In the vast majority of pocket universes where life cannot exist, there are no observers to wonder about the fine-tuning of physical constants. The apparent design of our universe is thus an observational selection effect, rather than evidence for actual design. But eternal inflation raises profound questions about the nature of probability and existence. If there are infinitely many pocket universes, and if every possible combination of physical laws occurs somewhere in the multiverse, then everything that can happen, and will happen infinitely often. There would be infinitely many universes exactly like ours, infinitely many that differ in small ways, and infinitely many that are completely different. This leads to puzzling questions about identity and uniqueness. If there are infinitely many versions of you living in infinitely many nearly identical universes, which one is the real you? Do all these copies have equal claim to existence? And what does it mean to say that you are experiencing this particular universe rather than one of the infinite copies? These questions push us to the very limits of what it means to exist and what it means to be conscious. In an infinite multiverse, every possible story gets told, every possible life gets lived, every possible thought gets thought. The uniqueness we feel as individuals becomes an illusion when viewed from the perspective of eternal inflation. The theory also challenges our notions of cosmic purpose and meaning. If everything that can happen does happen somewhere in the multiverse, then there is no single cosmic story, no unique evolutionary path, no special destiny for consciousness or life. Every possible meaning exists alongside every possible meaninglessness, every cosmic triumph alongside every cosmic tragedy. Yet perhaps there is a deeper kind of meaning to be found in this vision. Eternal inflation suggests that existence itself is endlessly creative, constantly exploring every possibility, giving rise to every conceivable form of beauty, complexity, and consciousness. In this view, we are not accidents in a purposeless universe, but rather expressions of the infinite creativity built into the very structure of reality. The mathematical description of eternal inflation emerges from our best current theories of particle physics and cosmology, but it pushes these theories to their limits and beyond. The idea involves extrapolating from processes we can observe in our pocket universe to a much larger realm that may be forever beyond direct observation. This raises questions about whether eternal inflation should be considered science in the traditional sense. How can we test a theory that predicts the existence of infinitely many unobservable universes? Some physicists argue that eternal inflation makes specific predictions about the properties of our observable universe, predictions that can be tested through careful observation of the cosmic microwave background radiation and other features of our cosmos. Others suggest that the theory should be evaluated based on its mathematical elegance and its ability to solve outstanding puzzles in cosmology, even if it cannot be directly tested. In this view, eternal inflation is valuable because it provides a coherent framework for understanding why our universe has the properties we observe. Still others worry that eternal inflation is more philosophy than physics, a speculative extrapolation that goes far beyond what our current evidence can support. They argue that science should focus on what can be observed and tested rather than constructing elaborate theories about unobservable realms. These debates reflect deeper questions about the nature of scientific knowledge and the limits of human understanding. As we probe the deepest mysteries of existence, we inevitably encounter questions that may be forever beyond the reach of direct observation. The challenge is to distinguish between scientifically motivated speculation and mere fantasy. Despite these uncertainties, eternal inflation has captured the imagination of physicists and the public alike because it offers such a radically different perspective on existence. It suggests that our universe is not all there is, but rather one small part of something unimaginably larger and more complex. In the eternally inflating multiverse, the Big Bang that created our universe was not the beginning of everything, but simply one event among infinitely many. Space and time were not created from nothing, but emerged from a deeper process that has been ongoing for eternity. The ultimate mystery is not why there is something rather than nothing, but why there is this particular something rather than all the other possible somethings. This vision places us in a cosmos of infinite scope and infinite creativity. We are not the center of existence, nor are we insignificant specks in an indifferent void. We are participants in an eternal cosmic process that constantly gives rise to new realities, new possibilities, and new forms of consciousness. As we float through the night on our small planet, orbiting our ordinary star in our typical galaxy, we might remember that we are also riding the expansion of space itself as it carries us through the vast arena of eternal inflation. Our entire universe is expanding within a larger multiverse that is expanding even faster, creating room for infinitely many other universes to be born. In this picture, existence is not a rare accident, but a fundamental feature of reality. The creative process that gave birth to our universe is ongoing, eternal, and inexhaustible. Somewhere in the vast expanse of eternally inflating space, new universes are being born at every moment, each carrying within it the potential for new forms of matter, energy, structure, and consciousness. The mystery of why there is something rather than nothing transforms into the mystery of why reality is so endlessly creative, so infinitely fertile, so constantly engaged in the process of bringing new possibilities into existence. In the eternal dance of cosmic inflation, in the endless birthing of new universes, we glimpse something that might be the deepest truth about existence itself, that being is inherently creative, inherently generous, inherently committed to exploring every possible way that reality can unfold. Look up at the night sky and consider what you see. Thousands of stars scattered across the darkness, each one a sun like ours, many of them accompanied by their own families of planets. Our galaxy alone contains hundreds of billions of such stars, and there are hundreds of billions of galaxies stretching across the observable universe. The scale is already beyond human comprehension, yet what if this vast cosmos we call our universe is itself just one among many, perhaps infinitely many? This is the profound possibility suggested by multiverse theory, the idea that our entire observable universe, with all its galaxies, stars, and planets, might be just one bubble in an infinite ocean of other universes. Each of these universes could have its own Big Bang, its own evolutionary history, its own laws of physics, and its own possibilities for life and consciousness. The concept of multiple universes emerges naturally from several different areas of modern physics and cosmology. We have already explored how eternal inflation might constantly create new pocket universes within an ever-expanding multiverse. But there are other ways that multiple universes might exist, each suggesting a different kind of multiverse with its own remarkable properties. Consider what happens when we take the mathematics of quantum mechanics seriously. In the standard interpretation of quantum mechanics, when a quantum system can exist in multiple states simultaneously, the act of measurement somehow causes it to collapse into one definite state. But this process of collapse has always been mysterious. What exactly causes it? Why does the system choose one state rather than another? Some physicists have proposed a radical solution to this puzzle. Perhaps quantum systems never actually collapse into single states. Perhaps every possible outcome of every quantum measurement actually occurs, but in different, parallel universes. When you observe a quantum particle that could be spinning either up or down, both outcomes happen. The universe splits into two branches, one where you observe spin up and another where you observe spin down. This is the many worlds interpretation of quantum mechanics, and it leads to a multiverse of staggering proportions. Every quantum event, from the decay of a radioactive atom to the absorption of a photon by your eye, splits reality into multiple branches. Each branch represents a different possible outcome, and each branch continues to evolve and split further as more quantum events occur. In this quantum multiverse, there are versions of you reading these words in universes where every possible quantum outcome has occurred differently. There are universes where the dinosaurs never went extinct, where World War II had a different outcome, where you made different choices at every moment of your life. Every possible history, no matter how unlikely, plays out somewhere in the vast branching structure of quantum reality. The number of these parallel universes grows exponentially with each passing moment. Every time a quantum event occurs anywhere in the universe, reality splits again, creating new branches of possibility. The total number of parallel universes quickly becomes so large that it defies description, yet each one is as real and valid as our own. But quantum mechanics is not the only source of multiple universes. String theory, our most promising attempt to unify all the forces of nature, also suggests the existence of multiple universes, though for very different reasons. In string theory, the fundamental building blocks of reality are not point particles, but tiny vibrating strings existing in a space-time that has more than the 4 dimensions we experience. These extra dimensions are thought to be curled up or compactified in ways that we cannot directly observe. But there are many different ways that extra dimensions can be compactified, and each different compactification leads to a universe with different laws of physics. The number of possible compactifications is enormous, perhaps 10 to the 500th power or more. Each of these compactifications represents a different possible universe with its own unique set of physical laws. In some of these universes, gravity might be much stronger than in ours. In others, the electromagnetic force might work differently, or there might be additional forces that do not exist in our universe at all. The diversity of possible universes in the string theory multiverse is truly staggering. These string theory universes might not just be mathematical abstractions. Some versions of string theory suggest that all of these possible universes actually exist somewhere in a vast higher dimensional space called the landscape. Our universe occupies one small region of this landscape, with its own particular combination of physical laws, while other universes occupy other regions with their own laws. The landscape of string theory connects with the ideas of eternal inflation in remarkable ways. If eternal inflation is constantly creating new regions of space-time, and if these regions can have different compactifications of extra dimensions, then eternal inflation might be populating the string theory landscape with actual universes. Each new pocket universe, created by inflation, might randomly select a different set of physical laws from the vast menu of possibilities. This leads to a multiverse that is both infinite in extent and infinite in diversity. Not only are there infinitely many universes, but these universes explore the full range of possible physical laws. Every conceivable way that matter and energy can behave, every possible set of fundamental forces, every imaginable structure of space and time, all exist somewhere in this ultimate multiverse. The implications of such a multiverse are profound and unsettling. If every possible universe exists, then the apparent fine-tuning of physical constants in our universe becomes much less mysterious. We observe a universe with laws that allow for the existence of stars, planets, and life, not because these laws were specially chosen, but because we could only evolve in a universe where such laws happen to apply. In the vast majority of universes in the multiverse, the laws of physics would not permit the existence of stable stars. In some, gravity would be too weak to pull matter together into dense concentrations. In others, gravity would be so strong that any concentration of matter would immediately collapse into black holes. In still others, the nuclear forces would be unable to hold atomic nuclei together, making chemistry impossible. Only in a tiny fraction of all possible universes would the laws of physics be just right for the formation of galaxies, stars, planets, and eventually life. But in an infinite multiverse, even a tiny fraction represents infinitely many universes. We find ourselves in one of the rare life-supporting universes, simply because that is the only kind of universe where observers like us could exist. This anthropic explanation for fine-tuning is both elegant and deeply troubling. It resolves the puzzle of why our universe seems designed for life, but it does so by making our universe infinitely less special. We are not the product of cosmic design or purpose, but simply the inevitable result of an infinite exploration of possibilities. The multiverse also raises profound questions about the nature of existence and consciousness. If there are infinitely many versions of you living in infinitely many different universes, which one is the real you? Are all these versions equally real, or is there something special about the particular version that you experience as yourself? Some philosophers have argued that the multiverse makes the concept of personal identity meaningless. If every possible version of your life is being lived out somewhere in the multiverse, then there is nothing unique about your particular experience. You are not a single person living one life, but rather a vast collection of similar people living similar lives across countless parallel realities. Others suggest that consciousness might provide a way to distinguish between different versions of yourself. Perhaps your subjective experience, the inner awareness that you have of being you, is somehow special and picks out one particular branch of the multiverse as the real one. But this view faces its own difficulties, since it requires consciousness to have properties that seem to go beyond what physics can currently explain. The multiverse also challenges our understanding of scientific explanation and prediction. If every possible outcome occurs somewhere in the multiverse, then in some sense, anything can happen, and everything does happen. This makes it difficult to use the multiverse to make specific predictions about what we should observe in our particular universe. Some critics argue that the multiverse is not really a scientific theory at all, but rather a philosophical speculation that cannot be tested or verified. How can we ever hope to observe other universes that exist beyond the boundaries of our own space-time? If we cannot observe other universes, then how can we claim that they exist? Defenders of multiverse theory respond that science has always involved theoretical entities that cannot be directly observed. We believe in atoms not because we can see them directly, but because atomic theory explains and predicts a wide range of observable phenomena. Similarly, multiverse theory might be valuable because it emerges naturally from our best theories of physics and helps explain puzzling features of our observable universe. The question of whether other universes exist is thus not just a scientific question but also a philosophical one. It forces us to think carefully about what kinds of entities we are willing to accept as real and what kinds of evidence we require for their existence. It challenges us to consider whether the boundaries of reality coincide with the boundaries of what we can observe. Despite these challenges, the idea of multiple universes continues to captivate scientists and the public alike. Part of the appeal lies in the sheer audacity of the concept. The multiverse represents the ultimate expansion of our cosmic perspective, suggesting that everything we can see and know is just the tiniest fraction of all that exists. There is also something deeply democratic about the multiverse. In a single universe, we might feel special or unique, chosen by some cosmic design to be the sole witnesses to existence. But in an infinite multiverse, every possible story gets told, every possible life gets lived, every possible dream gets fulfilled somewhere. The multiverse is infinitely inclusive, denying special status to any particular reality while embracing all possible realities. The multiverse also offers a kind of cosmic comfort. In our everyday lives, we are haunted by roads not taken, by choices not made, by possibilities unexplored. The multiverse suggests that somewhere, all these alternative paths are being explored. Every life you might have lived is being lived by some version of you in some parallel universe. Yet this comfort comes with its own form of existential vertigo. If every possible version of your life exists somewhere, then what makes your particular experience special? Why should you care about the choices you make if every possible choice is being made by some version of you? The multiverse offers infinite possibility, but also infinite dilution of meaning. Perhaps the deepest implication of multiverse theory is what it suggests about the nature of existence itself. In a single universe, existence might seem rare and precious, a delicate flame of consciousness flickering in an otherwise dark and empty cosmos. But in an infinite multiverse, existence becomes the fundamental condition of reality. Everything that can exist does exist. Everything that can happen does happen. This transforms our understanding of what it means to be. We are not unlikely accidents clinging to existence in an indifferent universe, but rather inevitable expressions of the infinite creativity built into the structure of reality itself. Consciousness and life and intelligence are not rare exceptions to the cosmic rule, but natural consequences of exploring all possible ways that matter and energy can organize themselves. As we contemplate the possibility of infinite other universes, we are led to a remarkable conclusion. Whether or not the multiverse actually exists, the very fact that we can conceive of it reveals something profound about the nature of mind and reality. We are beings capable of imagining infinities, of contemplating possibilities beyond all possible experience, of grasping concepts that transcend the boundaries of our own existence. In considering the multiverse, we are participating in the deepest human quest to understand our place in the cosmic order. We are using the remarkable gift of consciousness to explore not just what is, but what might be, not just the reality we inhabit, but all the possible realities that could exist. In this quest, we touch something that might be the most fundamental mystery of all: why reality is so rich, so creative, and so endlessly surprising in its capacity to give rise to minds that can wonder about it all. In the beginning was energy, pure, undifferentiated, creative energy that contained within itself the potential for everything that would ever exist. This energy was not something that existed within space and time, but rather the very substance from which space and time themselves would crystallize. It was the raw material of creation, the fundamental essence from which all the complexity and beauty of our universe would eventually emerge. To understand how our universe came to be, we must understand the profound relationship between energy and matter, a relationship that Einstein revealed to us in the most famous equation in all of science, E equals mc squared. This simple equation tells us that energy and matter are not separate things, but rather different forms of the same underlying reality. Matter is simply energy that has taken on a stable, persistent form, while energy is matter that has been liberated from the constraints of form. In the earliest moments of the universe, when temperatures soared beyond imagination and densities reached impossible extremes, the distinction between matter and energy became meaningless. Everything existed in a state of pure energy, a seething plasma where particles and antiparticles constantly materialized and annihilated each other in an endless dance of creation and destruction. As the universe expanded and cooled, this primordial energy began to condense into the first stable forms of matter. Just as steam condenses into water droplets when it cools, the energy of the early universe condensed into particles as temperatures dropped below critical thresholds. This was not a gradual process, but a series of dramatic phase transitions, each one fundamentally altering the nature of reality. The first of these transitions occurred when the universe was only a tiny fraction of a second old. As the temperature dropped below about 1 trillion degrees, the unified forces that had governed the earliest moments began to separate into the distinct fundamental forces we observe today. Gravity, which had been unified with the other forces in the first moments, became a separate force, forever destined to be much weaker than its siblings. This separation of forces was like the breaking of a perfect crystal, a cosmic symmetry breaking that released enormous amounts of energy and set the stage for all the complexity that would follow. the universe suddenly became a place where different forces could act independently, where gravity could pull matter together while electromagnetic forces could push it apart, where the strong nuclear force could bind particles into nuclei, while the weak nuclear force could cause them to decay. As the universe continued to expand and cool, more phase transitions followed. When the temperature dropped to about 100 billion degrees, the strong and weak nuclear forces separated from the electromagnetic force. This electro-weak phase transition was another moment of cosmic symmetry breaking, another release of energy that helped drive the expansion of space itself. During these early phase transitions, the universe was filled with exotic particles that no longer exist today, except in the most extreme astrophysical environments. There were particles that carried massive amounts of energy, particles that could convert directly into pure light, particles that existed only as virtual fluctuations in the quantum foam. The early universe was a cosmic laboratory where nature experimented with every possible form that matter and energy could take. But perhaps the most remarkable feature of this early cosmic evolution was how the total energy of the universe was conserved throughout all these dramatic changes. Energy could change form, from pure radiation to massive particles to the kinetic energy of expansion itself, but the total amount of energy remained constant. This conservation of energy provides one of the deepest clues about the nature of cosmic creation. Consider what this means for our understanding of how the universe began. If energy cannot be created or destroyed, only transformed from one form to another, then where did all the energy in the universe come from? How could the Big Bang have created the enormous amount of energy contained in every star, every galaxy, every particle of matter in the observable cosmos? The answer to this puzzle may lie in a profound insight about the nature of gravitational energy. Unlike other forms of energy, gravitational energy is negative. When two masses are pulled together by gravity, they lose gravitational potential energy, but this energy does not disappear. Instead, it is converted into other forms, such as kinetic energy or heat. This suggests a remarkable possibility. Perhaps the total energy of the universe is actually zero. All the positive energy contained in matter, radiation, and the motion of cosmic expansion might be exactly balanced by the negative energy of gravitational attraction. If this is true, then the universe could have emerged from nothing without violating the law of energy conservation. In this picture, the Big Bang was not the creation of energy from nothing, but rather the separation of a perfectly balanced nothing into positive and negative components. The universe borrowed energy to create matter and radiation, but it paid back this debt by creating an equal amount of negative gravitational energy. The total energy budget remained zero throughout the entire process. This zero-energy universe hypothesis provides an elegant solution to one of the deepest puzzles about cosmic creation. It suggests that the universe could have spontaneously emerged from a quantum fluctuation in the vacuum without violating any fundamental laws of physics. The quantum uncertainty principle allows for the temporary creation of energy from nothing, as long as the energy is paid back quickly enough. But if the universe has zero total energy, then the debt never needs to be repaid. As the universe continued to evolve, energy began to take on new and increasingly complex forms. During the era of Big Bang nucleosynthesis, the kinetic energy of cosmic expansion was converted into the binding energy that holds atomic nuclei together. Protons and neutrons, which had formed earlier from the energy of quantum fields, began to stick together to form the first light elements. This nuclear fusion process released enormous amounts of energy in the form of radiation, but it also locked up energy in the form of nuclear binding energy. The mass of a helium nucleus is slightly less than the mass of the four particles that compose it, and this missing mass represents energy that was released when the nucleus formed. This energy now contributes to the cosmic radiation that fills the universe. Later, as the universe continued to expand and cool, energy took on yet another form, the rest mass energy of stable atoms. When electrons finally combined with atomic nuclei during the era of recombination, they released their binding energy as photons, but they also became part of stable atomic structures that could persist for billions of years. These atoms became the building blocks for all the complex structures that would eventually emerge in the universe. But atoms are not just passive building blocks, they are repositories of energy. The mass of every atom represents energy that can potentially be released through nuclear reactions. Stars are cosmic furnaces that tap into this energy, converting a tiny fraction of their mass into the light and heat that illuminate the cosmos. The formation of stars represents another crucial phase in the cosmic evolution of energy and matter. Gravity, the weakest of the fundamental forces, finally got its chance to play a leading role. Over millions of years, gravity slowly gathered the primordial hydrogen and helium into ever denser concentrations. As these concentrations grew more massive, they began to heat up due to the gravitational potential energy being converted into kinetic energy. When the temperature and pressure at the center of these gas clouds became high enough, a new kind of energy transformation began. Nuclear fusion ignited, converting hydrogen into helium and releasing tremendous amounts of energy in the process. For the first time since the Big Bang nucleosynthesis, the universe began creating new sources of energy through nuclear reactions. Stars are remarkable energy converters. They take the gravitational potential energy of gas clouds and convert it into nuclear binding energy, then convert that nuclear energy into electromagnetic radiation. This radiation travels across space, carrying energy from the stellar core to the furthest reaches of the cosmos. Some of this energy eventually reaches planets like Earth, where it drives weather patterns, ocean currents, and the chemistry of life itself. But stars do more than just convert energy from one form to another. They also create new kinds of matter. In their nuclear furnaces, they forge elements heavier than hydrogen and helium, building up the periodic table one nuclear reaction at a time. Carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements are all products of stellar nucleosynthesis. When massive stars exhaust their nuclear fuel, they undergo catastrophic explosions called supernovae. These explosions release more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime. The energy of supernovae is so intense that it can forge elements even heavier than iron, creating gold, platinum, uranium, and all the other heavy elements that cannot be produced in ordinary stellar cores. Supernovae also play a crucial role in distributing energy and matter throughout the universe. The explosion disperses the elements created in the stellar core across vast regions of space, enriching the interstellar medium with the raw materials needed for planet formation and life. The energy of the explosion creates shock waves that can trigger the formation of new stars, continuing the cosmic cycle of creation. The supernova explosions that scatter heavy elements also create some of the most exotic objects in the universe, neutron stars and black holes. These remnants of stellar death represent matter and energy in their most extreme forms. A neutron star contains more mass than our Sun, compressed into a sphere only about 20 kilometers across. The density is so extreme that a teaspoon of neutron star material would weigh as much as a mountain. Black holes represent the ultimate triumph of gravity over all other forms of energy. When matter falls into a black hole, its mass energy becomes inaccessible to the outside universe, seemingly lost forever. Yet even black holes are not permanent repositories of energy. Stephen Hawking showed that black holes actually radiate energy through quantum processes at their event horizons, slowly evaporating over vast periods of time. The Hawking radiation from black holes represents one of the most profound connections between energy, matter, and the quantum nature of reality. It shows that even the most extreme gravitational objects are subject to quantum laws, and that energy can be extracted from apparently empty space through quantum processes. As we trace the evolution of energy and matter from the Big Bang to the present day, we see a story of increasing complexity and organization. Energy that began in a simple, unified form has been transformed and reorganized countless times, giving rise to particles, atoms, stars, planets, and eventually life itself. Each transformation has created new possibilities for further complexity, new ways for energy to organize itself into patterns of ever greater sophistication. The four fundamental forces that emerged from the primordial unity have each played their own crucial role in this cosmic evolution. Gravity gathered matter into stars and galaxies, providing the large-scale structure of the universe. The electromagnetic force enabled atoms to form molecules, allowing for the rich chemistry that underlies life. The strong nuclear force bound protons and neutrons into stable atomic nuclei, making possible the elements heavier than hydrogen. The weak nuclear force enabled radioactive decay and certain types of nuclear reactions, helping to power the Sun and other stars. Together, These forces have woven energy and matter into the intricate tapestry of cosmic structure we observe today. From the largest galaxy clusters to the smallest subatomic particles, everything in the universe is an expression of energy organized by the fundamental forces of nature. Yet, even as we understand more about how energy and matter evolve to create the cosmos we observe, profound mysteries remain. Why do the fundamental forces have the particular strengths they do? Why is the universe so finely balanced between expansion and collapse? Why does energy seem to naturally organize itself into increasingly complex patterns? These questions point toward deeper truths about the nature of reality itself. Perhaps energy and matter are not just the building blocks of the universe, but expressions of some even more fundamental principle. Perhaps the tendency toward complexity and organization reflects an inherent creativity built into the very foundations of existence. As we contemplate the cosmic dance of energy and matter, we are led to a profound realization. We ourselves are expressions of this dance. Every atom in our bodies was forged in stellar cores, or primordial nucleosynthesis. Every thought we think is a pattern of energy flowing through the neural networks of our brains. We are not separate from the cosmic story of energy and matter, but rather its latest chapter, the universe becoming conscious of its own magnificent creativity. As we stand at the edge of our cosmic knowledge, gazing back through time toward the moment of creation itself, we must confront a humbling question that strikes at the very heart of human understanding. Can we ever truly know how the universe began? Are there fundamental limits to what conscious beings like ourselves can discover about the deepest nature of existence? This question is not merely academic. It touches on the most profound issues in philosophy and science, the nature of knowledge itself, the relationship between mind and reality, and the ultimate limits of human inquiry. As we have journeyed through theories of quantum fluctuations, eternal inflation, and multiverses, we have been pushing the boundaries of what can be known, testing the limits of both observation and imagination. Consider what we are attempting to do when we try to understand the origin of the universe. We are using minds that evolved within the universe to comprehend the process that gave birth to the universe itself. We are employing concepts that developed within space and time to grasp what might have existed before space and time began. We are using mathematics that emerged from human experience to describe realms that transcend all possible human experience. This creates a fundamental puzzle about the nature of scientific knowledge. Science has been remarkably successful at explaining the world around us, from the motion of planets to the behavior of subatomic particles. But this success has always depended on our ability to observe, experiment, and test our theories against reality. What happens when we venture beyond the boundaries of what can be observed? The cosmic microwave background radiation represents the earliest moment we can directly observe in the universe's history. This ancient light, released when the universe first became transparent about 380,000 years after the Big Bang, carries information about the conditions that existed at that time. But it tells us nothing directly about what happened in the first moments after the Big Bang, and absolutely nothing about what might have existed before the Big Bang began. As we trace cosmic history backward from this earliest observable moment, we enter increasingly speculative territory. The physics of the first 3 minutes after the Big Bang is based on well-tested theories of nuclear physics and can be checked against observations of element abundances in the universe. But the physics of the first second involves conditions so extreme that we cannot recreate them in any laboratory. When we go back to the first tiny fraction of a second, we enter the realm of cosmic inflation, a theory that explains many puzzling features of the universe, but involves energies and processes that are completely beyond direct observation. The inflaton field that supposedly drove inflation is purely theoretical. We have never detected it directly, and we may never be able to do so. As we push back even further, to the Planck time about 10 to the negative 43rd seconds after the Big Bang, we reach the fundamental limits of our current theories. At this point, quantum effects become so important that our classical understanding of space and time breaks down completely. We need a theory of quantum gravity to proceed further, but no such theory currently exists. Beyond the Planck time lies the ultimate mystery, the singularity itself, or whatever process gave birth to the Big Bang. Here, not only do our theories break down, but the very concepts we use to think about reality become meaningless. Time, space, causation, existence, all the fundamental categories of human thought may be inadequate to describe what occurred at the moment of creation. This suggests that there might be absolute limits to what human beings can know about the origin of the universe. These limits are not just practical difficulties that better technology might overcome, but fundamental constraints imposed by the nature of knowledge itself. We are finite beings trying to comprehend the infinite, temporal creatures, attempting to understand the eternal products of the universe, seeking to explain their own origin. Yet this is not necessarily a cause for despair. Throughout history, humans have repeatedly encountered apparent limits to knowledge, only to transcend them through new insights and methods. Medieval thinkers believed that the motions of the celestial spheres were beyond human understanding, yet Newton showed that the same laws that govern falling apples also govern the orbits of planets. 19th century scientists thought that the age of the Earth and the mechanism of evolution were forever beyond scientific inquiry, yet we now have detailed knowledge of both. Early 20th century physicists believed that the interior of atoms was unknowable, yet quantum mechanics has given us precise descriptions of atomic structure. Perhaps the limits we encounter when thinking about cosmic origins will also prove to be temporary. New mathematical tools, new physical theories, new ways of thinking about space and time might eventually allow us to penetrate mysteries that now seem impenetrable. The development of quantum mechanics in the early 20th century revealed aspects of reality that no previous human had imagined. Perhaps equally revolutionary insights await us in the future. Some physicists are optimistic that a complete theory of quantum gravity will eventually allow us to understand what happened at the moment of the Big Bang. String theory, loop quantum gravity, and other approaches to quantum gravity all suggest that the singularity predicted by general relativity is not real, but rather an artifact of our incomplete understanding. If these theories are correct, then the universe did not begin with a true singularity, but rather with some finite, though extremely dense and hot, initial state. This initial state might be describable using the laws of physics, even if those laws are very different from the ones we observe today. The moment of creation might turn out to be as comprehensible as any other physical process, once we develop the right theoretical framework. But even if we succeed in describing the initial state of the universe, deeper questions would remain. Why did the universe begin with that particular initial state rather than some other? Why do the laws of physics that govern cosmic evolution have the particular form they do? Why does anything exist at all rather than nothing? These questions point toward even deeper levels of mystery. Perhaps the laws of physics themselves are not fundamental, but emerge from more basic principles. Perhaps what we call physical reality is itself just one level in an infinite hierarchy of more and more fundamental descriptions. Each time we answer one question about the nature of existence, we might discover that we have only uncovered deeper questions. This suggests that the quest to understand cosmic origins might be fundamentally open-ended. There might always be new levels of mystery to explore, new questions to ask, new frontiers to cross. The universe might be not just stranger than we imagine, but stranger than we can imagine, containing depths of mystery that will forever exceed our capacity to fathom. Yet there is something profoundly meaningful about this endless quest for understanding. Even if we can never reach final answers about the origin of everything, the very attempt to understand transforms us and enriches our existence. In seeking to comprehend the cosmos, we develop new ways of thinking, new mathematical tools, new scientific methods that enhance our ability to understand ourselves and our place in the world. The scientific revolution that began with Copernicus and Galileo did not just change our understanding of astronomy. It transformed human culture, giving us new ways of thinking about authority, evidence, and truth. The development of quantum mechanics in the 20th century did not just revolutionize physics. It influenced philosophy, art, literature, and our understanding of the nature of reality itself. Similarly, our current efforts to understand cosmic origins are not just exercises in abstract theorizing. They are expanding the boundaries of human consciousness, challenging us to think in new ways about existence, causation, and meaning. Whether or not we ever solve the ultimate puzzle of why there is something rather than nothing, the attempt to solve it is transforming what it means to be human. There is also something beautiful about the idea that reality might contain mysteries that forever exceed our understanding. A universe that could be completely comprehended by finite minds might be a rather small and limited universe. A cosmos that contains infinite depths of mystery, endless frontiers for exploration, eternal sources of wonder and amazement, seems more worthy of the awe and reverence that the universe naturally inspires. Consider what it means that we, as conscious beings, can even ask questions about cosmic origins. We are arrangements of atoms that have become aware of themselves, patterns of matter and energy that can contemplate the source of matter and energy. We are the universe becoming conscious of itself, reality developing the capacity to question its own existence. This capacity for cosmic questioning might be one of the most remarkable features of existence. In a universe that began with simple energy and matter, complexity has evolved to the point where parts of the universe can wonder about the whole. Consciousness has emerged that can contemplate not just what is, but what might be, not just the actual but the possible. Perhaps this capacity for questioning is more important than any particular answers we might discover. The ability to wonder, to seek, to push beyond the boundaries of the known might be the most precious gift that cosmic evolution has produced. In our questioning, we participate in something larger than ourselves, a cosmic process of self-discovery that has been unfolding for nearly 14 billion years. The limits of human knowledge about cosmic origins are real and significant. We are finite beings embedded within the very reality we seek to understand. Our concepts, our language, our ways of thinking all evolved within the universe, and may be inadequate to describe the universe's ultimate source. Yet these limits are not barriers but invitations. They invite us to stretch our minds, to develop new ways of thinking, to push beyond the comfortable boundaries of familiar concepts. They remind us that reality is larger and stranger than we have yet imagined, that there are always new frontiers to explore, new mysteries to contemplate. In acknowledging the limits of what we can know about cosmic origins, we do not diminish the value of the quest, but rather honor its true depth and significance. We recognize that the questions we are asking touch the very foundations of existence itself. We acknowledge that in seeking to understand the origin of everything, we are participating in the deepest and most fundamental form of human inquiry. As we continue our journey through the cosmic mystery, we carry with us both humility about the limits of our understanding and wonder at the magnificent reality we seek to comprehend. Whether or not we ever fully solve the puzzle of cosmic origins, the very fact that we can pose such questions, that consciousness has evolved to the point where it can contemplate its own cosmic context, remains one of the most extraordinary features of the universe we inhabit. The origin of the universe may forever remain partially mysterious, but that mystery is not a failure of human knowledge, but rather a testament to the infinite depths and endless creativity of existence itself. In confronting the limits of what we can know, we touch something sacred about the nature of reality and our place within it. Here we stand, at the end of our cosmic journey, having traveled from the deepest concepts of nothingness to the farthest reaches of multiverse theory. We have explored quantum fluctuations and eternal inflation, singularities and symmetry breaking, the role of energy and matter in cosmic creation. Yet for all our exploration, for all the remarkable insights of modern physics and cosmology, the ultimate mystery remains as profound and beautiful as ever. Perhaps this is as it should be. Perhaps the deepest questions about existence are not meant to be solved, but to be lived with, contemplated, and appreciated for their inexhaustible depth. In our quest to understand what sparked the Big Bang, we have discovered something even more remarkable than any particular answer. We have discovered the infinite capacity of reality to surprise and amaze us. Think about what we have learned on this journey. We have seen that what appears to be empty space is actually alive with quantum activity, that virtual particles constantly pop into existence from the energy of the vacuum itself. We have discovered that our entire observable universe, vast beyond imagination, might be just one bubble in an infinite ocean of other universes, each with its own Big Bang and its own evolutionary story. We have learned that the familiar concepts of space and time, which seem so fundamental to our existence, might themselves be emergent properties that arose from something even more basic. We have contemplated the possibility that everything we know and love emerged from a quantum fluctuation so brief and so subtle that it exists at the very edge of what can be measured or imagined. These discoveries have not diminished the mystery of existence, but rather revealed it to be far grander and more intricate than our ancestors could have dreamed. Each answer we find opens up new realms of questions. Each boundary we cross reveals new horizons, stretching infinitely beyond our current understanding. This is the nature of infinite mystery. It is not a problem to be solved, but a reality to be explored. Not a puzzle with a final answer, but an endless invitation to deeper understanding. The mystery of cosmic origins is infinite, not because we lack sufficient information or clever enough theories, but because existence itself is infinitely creative, infinitely complex, infinitely surprising. Consider the remarkable fact that we can even contemplate these mysteries. We are arrangements of atoms that emerged from the Big Bang, patterns of matter and energy that have learned to wonder about their own cosmic history. We are the universe becoming conscious of itself, developing the capacity to question its own existence and marvel at its own creativity. This capacity for cosmic wonder might be one of the most extraordinary developments in the 13.8 billion year history of the universe. From simple hydrogen and helium atoms drifting through primordial space, complexity has evolved to the point where parts of the universe can contemplate the whole. Consciousness has emerged that can ask not just what exists, but why anything exists at all. In embracing the infinite mystery of cosmic origins, we are not giving up on understanding, but rather recognizing that understanding itself is an endless process. We are acknowledging that the questions we ask are as important as any answers we might find, that the capacity to wonder is as remarkable as any particular knowledge we might acquire. There is profound beauty in this perspective. It means that no matter how much we learn about the universe, there will always be new frontiers to explore, new mysteries to contemplate, new sources of wonder and amazement. The cosmos is not a finite puzzle that can be completely solved, but an infinite wellspring of mystery that will forever exceed our capacity to exhaust. This inexhaustibility of cosmic mystery is not a limitation but a gift. It means that conscious beings like ourselves will never run out of profound questions to ask, deep problems to solve, beautiful mysteries to explore. The universe has given birth to minds capable of endless inquiry, and it has provided an infinite arena for that inquiry to unfold. As we embrace this infinite mystery, we also embrace a kind of cosmic humility. We recognize that we are finite beings contemplating infinite questions, temporary patterns of matter and energy, seeking to understand eternal processes. Our knowledge, however extensive it might become, will always be a tiny island in an infinite ocean of the unknown. Yet this humility is not a source of despair, but of wonder. It reminds us that we are part of something vastly greater than ourselves, participants in a cosmic story that stretches from the Big Bang to an unimaginably distant future. We are not outside observers studying the universe from some external vantage point, but integral parts of the very reality we seek to understand. In contemplating the mystery of what sparked the Big Bang, we are participating in the universe's ongoing process of self-discovery. Every question we ask, every theory we develop, every insight we gain is the cosmos coming to know itself more deeply. We are not separate from the creative process that gave birth to the universe, but are its latest expression, its current attempt to understand its own nature. This perspective transforms our relationship with cosmic mystery. Instead of seeing the unknown as a barrier to be overcome, we can see it as an invitation to participate more fully in the universe's creative unfolding. Instead of feeling frustrated by the limits of our knowledge, we can feel grateful for the infinite depths that await our exploration. The mystery of cosmic origins connects us to the deepest questions that conscious beings have always asked. Why is there something rather than nothing? What is the nature of existence itself? How did consciousness emerge from unconscious matter? What is our place in the cosmic order? These questions have echoed through human history, asked by philosophers and mystics, scientists and poets, ordinary people gazing up at the night sky. In our modern scientific age, we have developed new tools for exploring these ancient questions, new languages for articulating our cosmic wonder. The mathematics of quantum mechanics and general relativity has given us precise ways to describe the behavior of matter and energy at the smallest and largest scales. Powerful telescopes have revealed the deep structure of space and time, showing us the universe as it existed billions of years ago. Yet for all our scientific sophistication, we find ourselves facing the same fundamental mysteries that have always confronted human consciousness. The questions have not been answered so much as deepened and enriched. We now know enough about the universe to appreciate just how mysterious it truly is. This deepening of mystery is one of the great achievements of modern science. By studying the cosmos with ever greater precision and sophistication, we have discovered that reality is far stranger and more wonderful than our ancestors imagined. We have learned that the universe is not a mechanical clockwork running according to simple laws, but a creative, evolving, self-organizing process of almost infinite complexity. The Big Bang itself embodies this strangeness. Here is an event that created space and time, that brought forth matter and energy from some primordial state that transcends our ordinary categories of thought. Here is a process that gave birth to everything we know and love, yet remains fundamentally mysterious despite decades of intensive study. As we embrace this mystery, we also embrace the ongoing adventure of cosmic discovery. Every new observation, every new theory, every new insight adds another chapter to the story of our understanding. We may never reach a final answer to the question of what sparked the Big Bang, but we will continue to discover new aspects of this ultimate mystery, new ways to appreciate its depth and beauty. The adventure of cosmic discovery is not just an intellectual exercise, but a deeply human endeavor that engages our whole being. When we contemplate the origin of the universe, we are not just exercising our rational faculties, but opening ourselves to experiences of awe, wonder, and reverence that touch the deepest parts of our humanity. There is something sacred about this encounter with cosmic mystery. In confronting questions that exceed our ability to fully answer, we touch something that transcends our ordinary experience. We connect with the infinite creativity that brought the universe into existence and continues to manifest in every moment of cosmic evolution. This sacred dimension of cosmic inquiry reminds us that science is not just a technical enterprise, but a form of spiritual practice, a way of opening ourselves to the deepest truths about existence. In studying the universe, we are not just gathering information, but participating in a process of cosmic communion, allowing ourselves to be transformed by our encounter with ultimate reality. As our journey through the mystery of cosmic origins draws to a close, we find ourselves not with final answers, but with a deeper appreciation for the questions themselves. We have learned that the universe is far more mysterious and wonderful than we ever imagined, and that we are privileged to be conscious participants in its ongoing story of self-discovery. The question of what sparked the Big Bang may never be fully answered, but that does not diminish its importance or beauty. In asking this question, we are exercising the most remarkable capacity that cosmic evolution has produced, the ability of matter to become conscious of itself, the power of the universe to contemplate its own existence. Whether the Big Bang emerged from quantum fluctuations or eternal inflation, from colliding brains or some process we have not yet imagined, the fundamental mystery remains. Why does anything exist at all? How does unconscious matter give rise to conscious beings? What is the ultimate nature of the reality we inhabit? These questions point us toward mysteries that may be infinite in depth, inexhaustible in their capacity to surprise and inspire us. In embracing these mysteries, we embrace our role as cosmic explorers, participants in the universe's ongoing adventure of self-discovery. As we rest beneath the stars tonight, we can remember that we are made of star stuff, that every atom in our bodies was forged in stellar cores or in the primordial fires of the Big Bang itself. We are not separate from the cosmic story, but part of it, not outside observers, but intimate participants in the greatest mystery of all, the mystery of existence itself. In this infinite mystery, we find not answers, but something even more precious, an endless source of wonder, an inexhaustible wellspring of beauty, and an eternal invitation to explore the deepest nature of the reality we are privileged to inhabit. The universe may have sparked into existence from nothing, but it has given birth to something infinitely precious, minds capable of contemplating the marvel of their own existence. And so we come to the end of our cosmic meditation, our gentle exploration through the deepest mysteries that existence has to offer. We have traveled together from the incomprehensible concept of absolute nothingness to the mind-expanding possibilities of infinite multiverses. We have contemplated quantum fluctuations and eternal inflation, pondered singularities and symmetry breaking, and reflected on the profound limits of human knowledge itself. Throughout this journey, one truth has remained constant. The universe is far more mysterious, far more beautiful, and far more creative than our human minds can fully comprehend. What began as a simple question about what sparked the Big Bang has led us into realms of thought that stretch the very boundaries of imagination. Perhaps this is the most profound lesson of our exploration. The deepest questions do not always yield simple answers. Instead, they open doorways into ever greater mysteries, revealing layer upon layer of cosmic complexity and beauty. In seeking to understand the beginning of everything, we have discovered that the beginning itself might be a concept that transcends our ordinary ways of thinking about time, causation, and existence. We have learned that nothingness might not be empty but full of potential, that the quantum vacuum teems with invisible activity, and that space and time themselves might emerge from something even more fundamental. We have glimpsed the possibility that our entire universe is just one note in an infinite cosmic symphony, one bubble in an endless ocean of realities. Yet for all our scientific sophistication, for all the remarkable insights of modern physics and cosmology, we find ourselves in much the same position as our ancestors who first looked up at the night sky and wondered about their place in the cosmic order. We are finite beings contemplating infinite mysteries, temporary patterns of matter and energy, seeking to understand eternal processes. This is not a failure of human understanding, but perhaps its greatest triumph. In recognizing the limits of what we can know, we also recognize the infinite depths of what remains to be explored. The universe has given birth to minds capable of asking questions that exceed their ability to answer, consciousness that can contemplate mysteries beyond its capacity to solve. As you settle into rest tonight, consider the remarkable fact that you are part of this cosmic story. Every breath you take contains atoms that were forged in stellar cores billions of years ago. Every thought you think is a pattern of energy flowing through neural networks that emerged from the same cosmic processes that gave birth to galaxies and stars. You are not a separate observer of the universe, but an integral part of its ongoing evolution. You are the cosmos becoming conscious of itself, matter that has learned to wonder about its own existence. In your capacity for cosmic questioning, you participate in the deepest and most beautiful aspect of reality, its endless creativity and its infinite potential for self-discovery. The question of what sparked the Big Bang may never receive a final answer, but that does not diminish its importance or beauty. The very fact that such questions can be asked, that consciousness has evolved to the point where it can contemplate the origin of everything, remains one of the most extraordinary developments in the entire history of the universe. From the emptiness of nothingness, if such emptiness ever existed, or from the quantum foam of eternal creativity, the universe burst into existence with a violence and beauty that defies description. In that first moment, space and time were born, matter and energy emerged, and the stage was set for everything that would follow. 13.8 billion years later, arrangements of matter and energy that began as simple hydrogen and helium have evolved into beings capable of love, art, music, poetry, and science. The universe has given birth to minds that can contemplate not just what is, but what might be, not just the actual but the possible. In the vast cosmic web of galaxies and dark matter, on a small planet orbiting an ordinary star in an unremarkable galaxy, consciousness has emerged that can ask the ultimate questions about existence itself. This consciousness is you, and it is every human being who has ever wondered about their place in the cosmic order. As you drift into sleep tonight, you can rest in the knowledge that you are held by the same forces that shaped the cosmos from its earliest moments. Gravity, which gathered the first stars from primordial gas clouds, now holds you gently to the surface of our planet. The electromagnetic force, which enables atoms to bond into molecules, allows your body to maintain its structure and your brain to process thoughts and dreams. The nuclear forces that bind protons and neutrons in atomic nuclei provide the stability that makes complex chemistry possible, enabling the intricate molecular processes that sustain life. Even the expansion of space itself, which began with the Big Bang and continues today, is part of the cosmic context within which your existence unfolds. You are not an accident in an indifferent universe, but a natural expression of cosmic creativity, a manifestation of the same processes that gave birth to stars and galaxies. The capacity for wonder that you carry within you is itself a cosmic phenomenon, matter organized in such a way that it can contemplate its own cosmic history. The search for understanding that brought us together tonight is part of an ancient and ongoing human quest that stretches back to the first conscious beings who looked up at the night sky and wondered about their origins. This quest will continue long after our individual lives have ended, carried forward by future generations who will ask new questions and discover new mysteries. Perhaps they will solve some of the puzzles that remain mysterious to us. Perhaps they will develop theories of quantum gravity that reveal what really happened at the moment of the Big Bang. Perhaps they will discover evidence for other universes or find ways to test the predictions of eternal inflation. But even if they answer some of our current questions, they will surely discover new mysteries that we cannot even imagine. The universe seems to have an inexhaustible capacity to surprise and amaze those who study it carefully. Each new discovery reveals new depths of complexity and beauty that were previously hidden from view. This endless unfolding of cosmic mystery is one of the most beautiful aspects of existence. It means that the adventure of discovery need never end, that there will always be new frontiers to explore, new questions to ask, new sources of wonder to contemplate. The cosmos is not a finite puzzle that can be completely solved, but an infinite wellspring of mystery and beauty. As the night deepens around you and the stars wheel overhead in their ancient patterns, you can remember that you are connected to all of this cosmic grandeur. The photons of starlight entering your eyes have traveled across vast distances and enormous spans of time to reach you. You are receiving messages from stellar furnaces that may have been shining since before our solar system formed. The darkness between the stars is not empty but filled with the cosmic microwave background radiation, the afterglow of the Big Bang itself. This ancient light, stretched and cooled by billions of years of cosmic expansion, surrounds you at every moment, a gentle reminder of the universe's fiery birth. In this cosmic context, your dreams tonight become part of the universe, dreaming about itself. Your unconscious mind, processing the experiences of the day and weaving them into new patterns and possibilities, participates in the same creative process that has been unfolding since the first moment of existence. The questions that have guided our exploration tonight, the sense of wonder and mystery that drew us into contemplation of cosmic origins, these are not just human experiences, but cosmic phenomena. They represent the universe developing the capacity to question its own existence, to marvel at its own creativity, to seek understanding of its own deepest nature. Whether the Big Bang emerged from quantum fluctuations or eternal inflation, from colliding brains, or some process we have yet to imagine, the fundamental miracle remains. From whatever came before, whether it was nothing or something we cannot comprehend, the universe has given birth to beauty, complexity, consciousness, and love. In your capacity to wonder about these mysteries, you embody this cosmic miracle. You are proof that the universe is not just a collection of matter and energy following mechanical laws, but a creative, evolving, self-organizing process capable of giving birth to minds that can appreciate its own magnificence. Rest now beneath the quiet stars, knowing that the mysteries will continue to unfold long after this night has passed. The search for understanding that brought us together will continue across generations, carried forward by countless curious minds drawn to contemplate the deepest questions about existence. From the emptiness of nothingness, or from depths of creativity we cannot fathom, the universe burst into existence and began its long journey toward complexity, beauty, and consciousness. Tonight, you are part of that journey, a participant in the ongoing cosmic story of self-discovery. Sleep well, cosmic wanderer, dream of infinite possibilities, and remember that in your dreaming, the universe continues its eternal exploration of what it means to exist.